My friends, I'm going to walk you through some killer exam problems that involve heat capacity, specific heat, and heat transfer. These are problems in thermodynamics that are geared towards a general chemistry class or a general physics class or whatnot. So this is the warm-up, and just to get us started, and the warm-up goes, how much energy is needed to increase the temperature of 45 grams of water from 15 degrees Celsius to 35 degrees Celsius? And we're given the specific heat of water. So the specific heat tells us how much energy is required to raise the temperature by 1 degree of 1 gram. So this says 4.186 joules of energy is required to increase the temperature of 1 gram of water by 1 degree Celsius. Okay, so we'll start off with our equation, mc delta T, and I call this the MCAT equation because it looks like MCAT. So there's 45 grams of water, and the specific heat is 4.186. It's nice to put the units in just so we can see it all cancels. Grams, degrees Celsius, and the change in temperature, we're going from 15 degrees Celsius, that's the initial temperature, to 35 degrees Celsius, that's the final temperature. So it's 35 degrees Celsius minus 15 degrees Celsius. And we'll plug that into our calculator. 45 times 4.186 times 35 minus 15, and that looks good. 3767.4. 3767.4, but we only have two sig figs. And let's see if our units work. Grams cancel, degrees Celsius cancel, so this is in joules. So 3,800 joules of energy as heat is required to increase the temperature of this water. Okay, next warm up. We have a 1 kilogram bucket of sand and 1 kilogram bucket of water, and each bucket is at 25 degrees Celsius. Let's draw a little picture here. Here's our water, and it's at 25 degrees Celsius, and yeah, this is water. I'll just say H2O, and then we have another one of sand. This is our sand, also at 25 degrees Celsius, and we'll just write, maybe I'll just write sand in there. Each receives 125 kilojoules of heat. So imagine we have like a fire down here or a burner, and we have 125 kilojoules of heat going into it. So we're heating it up the same amount. We want to know what the final temperature of each substance is. And if you've ever gone to the beach and when it's really, really hot and sunny, you'll find that obviously the water or the sand is a lot hotter than the water. Now there's more water than sand as well, but it could have something to do with the heat capacity. Let's check that out. So let's find out what the final temperature is. And we have these heat capacities here. So let's start off with the water. So for the water, we have our MCAT equation, mc delta T, and we're putting in 125 kilojoules. So 125, now there's 1,000 kilojoules in a joule. So we got to say times 10 to the 3 joules because we want to be in joules. And how much do we have? We have 1 kilogram, which is 1,000 grams. We want to be in grams because specific heat is in grams. And the specific heat of water is 4.186 grams. Oh, no, not grams. Joules per gram degrees Celsius. And we have some final temperature, which we don't know, minus the initial temperature, which is 25 degrees Celsius. Okay, so joules cancel and grams cancel, and our temperature will be in degrees Celsius. So we're just going to, I'm going to take this number and I'm going to divide by 1,000 and times 4.186. So 1,000 times 4.186, so that this cancels out, and we'll just kind of simplify it a little bit. So 125 times 10 to the power of 3 divided by, make sure we have brackets there, times 4.186, 29.861. So on the left-hand side, we have 29.861. Is that right? 29.861. Okay. We're going to be in degrees Celsius. This degrees Celsius would be here. So I'll just write degrees Celsius. And then on the right-hand side, all this stuff's gone. So we have final temperature minus 25 degrees Celsius. So we just need to add 25 degrees Celsius to the other side. So I'll just take the same number as before, plus 25, right? We got to add, you see that, I hope. Do you see this? You just got to add 25 degrees Celsius to both sides. Okay, and then our final temperature is 54.86. So T final, I'll write it over here. T final equals 54.86 degrees Celsius. We only have 2 sig figs, so essentially 55 degrees Celsius is the final temperature of the water. Okay, now for the sand. Let's see how hot the sand gets. We use the same equation, Q equals mc delta T, and we have a kilogram of sand, so that's 1,000 grams. The heat capacity is 0.800, 0.800 joules per gram degrees Celsius. We want to know what the final temperature is. The initial temperature is 25 degrees Celsius. Is it 25 or 25.0? 25. Okay. And it received 125 kilojoules of heat. So over here we'll have 125 times 10 to the 3 joules. Now we're going to do this exact same equation, same thing we did before, where we'll just divide by these. And so I won't kind of write those steps there. Oh, actually, can I reuse this? I'll write it out again. 125 times 10 to the power of 3 divided by 1,000 times 0.8. Oh, divided by, try again, 125. That's why I like these calculators, because I can see if I made an error when I'm typing. I strongly recommend getting a calculator with at least 2 lines. Those single liners I don't like, because it's hard to see if you made an error. Okay, so I divided by this, and then I'm going to plus 25 degrees Celsius, just like I did last time here. Plus 25 degrees is, whew, holy, 181. I should close my brackets here. But if we solve for TF, we get 181 and change, which is not significant for digits, degrees Celsius. We have 25. Yeah, so 181 degrees Celsius. I was just looking at the sig figs. The sand is a lot hotter than the water. And if we look at this here, the same amount of sand, so 1 kilogram, the same amount of sand will be significantly hotter than water, even though both of them get heated by the same amount of energy. The same amount of heat transfer goes through, but the water doesn't heat up as much because it has a higher heat capacity. So that's pretty cool. All right, this is our first exam problem. A 75-gram block of iron at 300 degrees Celsius is dropped into a 500 milliliter flask of water at 5 degrees Celsius. Before we kind of read the rest of it, let's draw what's going on. So we have 500 milliliter flask of water. This is water, and it's at 5 degrees Celsius. Oh, that's Celsius. And we have a hot block of iron, 300 degrees Celsius, going into the water. Okay, and we want to know what the final temperature. So obviously they're going to warm up, and we're going to assume that we don't have any heat transfer to the surroundings. This is a bit unrealistic, but if we insulate it enough, we can approximate this to be true. Okay, now what's true is that, see this arrow? We have heat transfer going from the block of iron to the water. So we have this energy as heat going from the block of iron to the water. And the iron is losing Q energy, but the water is gaining that same amount of energy. The energy lost by the iron is gained by the water. So we can say that Q of the iron is going to be equal. Now this is negative, right? This is a negative number. So maybe I'll write this as the water first, just so it's a little less confusing. Q of the water. This is going to be a positive number because the water is gaining energy. So this is positive. Q of H2O, the heat transferred to water, is equal to the negative of the Q, the heat transferred from the iron here, because the iron is losing energy. And we can actually rearrange this equation. Q of the water plus Q of the iron, so the heat of the water plus the heat transferred away from the iron, that has to equal 0. So what's lost by the iron is gained by the water, and it just happens that this energy is heat. This heat for the iron is going to be negative because it's losing energy, and this is going to be positive. And this is our general equation. This is where you always want to start when we have these type of heat transfer problems. And even with calorimetry, we're going to use this problem as well, this type of equation as well. This comes from the first law of thermodynamics. I can derive it if you want me to. Just let me know in the comments and I'll make a video on it. But we basically start here for the most part. Okay, so now we know from the warm-up questions what Q's are. So the Q's are mc delta T. This is going to be for the water. And we have an mc delta T. And that's going to, we have this for the iron. And all of that has to be 0. What's lost from the iron is gained by the water. We have, what's our mass of water? Oh, we don't have a mass. We have 500 mils. You may see this. So you have a volume of water. We have to assume that it has a density of 1. If they don't give us a density, it's usually a little bit less than 1. But we'll assume that the density of water is 1 gram for every 1 milliliter. So that this is essentially 500 grams of water. Okay, so we have 500 grams of water. 500 grams. The heat capacity of water is 4.186 joules per gram degrees Celsius. And the final temperature is what we want. The initial temperature is 5 degrees Celsius, nice and cold, plus the mass of the iron. What's the, it's 75 grams, so not too big of a block. 75 grams. And the heat capacity of iron is 0.462 joules per gram degrees Celsius. We want to know what the final temperature is. And we know the initial temperature is 300 degrees Celsius. And all this has to equal 0. Whoa. Get rid of that line there. Equals 0. Okay. These final temperatures have to be the same because when the iron is added to the water, they reach thermal equilibrium after all that heat transfer is done. Okay, so I'll do this first part here. So 500 times 4.186 is 2093. I will cancel out the grams. So 2093 joules per degree Celsius, TF minus 5 degrees Celsius, plus, I'll do the second part, 75 times 0.462 is 34.65. 34.65, and that's in joules per degree Celsius. And we have our temperature final, and our 300 degrees Celsius is still here, minus 300 degrees Celsius. So that equals 0. Okay, so we're going to feed the chickens. We're going to distribute this number, each of these numbers, into the brackets here. So this gives us 2093 joules per degree Celsius times the final temperature minus 5 times this number, which we'll figure out what that is, times 5, yeah, 10,465, so 10,465, this would be in joules, plus 34.65 joules per degree Celsius times T final minus, and we'll do this number times this number, so 34.65 times 300 is 10,395, 10,395 joules, because our degree Celsius cancels out. 0. Now we have common terms, so these are like terms because they both have T final in them. So we'll factor out T final, which gives us, so we'll get 2093. Actually, you know what? We won't even factor. We'll just add these two terms together. We'll take 2093 plus 34.65. It's 2128, 2127.6. 2127.665, I guess. Joules degrees Celsius, T final equals, now I'm going to add these together and then move them to the other side so they become positive, right? So this one plus this one, they're both negative, so it adds up, and then if we move them over, it becomes positive. So I'm just literally going to add these two numbers because they're going to be on the other side of the equation. I hope that's not confusing. So 2860 2860 joules. Okay, so our joules cancel out. Our degrees Celsius will come back up here. We're going to divide everything by this number, 2127.65. 2127.65, and then this degrees Celsius will go up here if we multiply both sides by degrees Celsius. So our final temperature will be in degrees Celsius. Hopefully it's under 100. If not, then we've boiled our water. Hopefully it's under 100 degrees Celsius. If not, then we've boiled our water. Okay, so 20860 divided by 2127.65 is, oh, it doesn't heat up that much at all, does it? Look at that, 9.80. I was expecting it to be a lot more, but we'll see why it makes sense. 9.804, 9.804 degrees Celsius. We really only have, well, where do we do a sig figs here? This is one sig fig. We'll assume this is 3, this is 2. If this is 2, then we have two sig figs here. This would be 2 sig figs. Then we'd only have this times this is 2. Wait, this would be 2 sig figs. I think we just have 2 sig figs. I'm going to go with 2 significant figures with this one. Really quick analysis. Let me know if I'm wrong. Okay, so the water only heats up to 9.8 degrees Celsius and the block together. Does that make sense? This is very, very hot. So shouldn't the temperature of the water go up more? It actually makes sense when we think about it because we have a lot of water. So a lot of water can absorb this energy. So we have heat transfer to a lot of water with a relatively small block. And the heat capacity of water is so much higher than iron that it doesn't take much energy to cool this iron down. The iron is going to cool down a lot faster than the water heats up because the heat capacity is higher. So the iron will cool down and heat up faster. If it needs to heat up, it'll heat up faster. If it needs to cool down, it'll cool down faster than the water will heat up. Okay, for this last one, we mix 100 grams of water at 15 degrees Celsius and 23 grams of water at 85 degrees Celsius in a styrofoam cup. So let's do that. So we have 100.0 grams of water here, which is in a styrofoam cup, and it's currently at 15 degrees Celsius. And then we're adding some hotter water. So we'll say this is the hot water, and there's 23.0 grams of it, and it's at 85 degrees Celsius. And we're going to add that into there. And yeah, so we have heat transfer from the hot water into the cold water. So that's losing energy as heat, negative Q. And then this water is going to warm up when we mix it together. Now we're in a cup calorimeter, and we want to know the final temperature of the sample. Well, we have heat transfer from the hot water to the cold water, but we also have heat transfer into the calorimeter as well. This is our calorimeter. So we have 3 heat transfers going on, 1, 2, and 3. And if we add up all of these heat transfers, they have to balance out to be 0, just like what we did last time. So we can say Q of the cold water plus Q of the hot water plus Q of the calorimeter has to equal 0. Now, our equation for Q is mc delta T. So we have an mc delta T for the cold water plus the mc delta T for the hot water plus now we don't have an mc delta T for the calorimeter. What we have is the heat capacity, and this is based on just temperature only. So there's no mass that we have to worry about. So it's just going to be this times the degrees Celsius times the change in temperature, because if we cancel out the degrees Celsius, we're left with joules, which is what we want for heat. So we'll have C cal times the change in temperature of the calorimeter. And all of that has to equal 0. Okie dokie, so the mass of the cold water, there's 100 grams. So we'll plug that in, 100.0 grams. The heat capacity of water is 4.186. 4.186. It's from a previous I remember that from a previous exam question. You'll probably be given this. You don't need to memorize it, but there it is. Joules per gram degree Celsius times the change in temperature. So we don't know what the final temperature is, but we do know that the initial temperature is 15 degrees Celsius, and the mass of the hot water is 23.0 grams. The heat capacity, it's still water, so we'll put in the same number, 4.186 joules per gram degrees Celsius. And its change in temperature will be whatever the final temperature is, that's what we're solving for, minus its initial temperature, 85 degrees Celsius, plus the heat capacity of the calorimeter, which is 14.3. 14.3 joules per degree Celsius. So just squeeze it in here. The change in temperature is now T final. We don't know what the final temperature is, but the initial temperature, it has to be 15 degrees Celsius because it has to be the same temperature as what this sample is. If it wasn't 15 degrees Celsius, say this calorimeter was a different temperature, if it was, then before we even add the hot water, we'd have heat transfer occurring. If the calorimeter was hotter, then we'd be warming up this water here. It wouldn't be at 15 degrees Celsius. It'd be warming up due to the hotter calorimeter before we even add this. So the sample here and the calorimeter should be in thermal equilibrium and should be at the same temperature. So 15 degrees Celsius. So all of that equals 0. Okay, gotta plug this in so that we don't have too many things going on. Oh, actually, I could do this. This is times 100, so this would just be 418.6, and our grams cancel out, so that's joules per degree Celsius times T final minus 15 degrees Celsius plus 23 times 4.186 is 96.278. So 96.278, and our grams cancel out again. It's always nice to cancel the units. Looks good so that we know our units are working out. T final minus 85 degrees Celsius plus, this is, now we'll kind of distribute this into the brackets. It's kind of squished in, but I hope you can see this. So 14.3 joules per degree Celsius times T final minus 14.3 times 15, what is that? 14.3 times 15 degrees Celsius to 14.5, so minus 214.5. And our degrees Celsius cancels out, so we're left with joules equals 0. Now I'm going to expand this and combine like terms. So this is a like term, this is a like term, and where did our T final? Oh yeah, this is a like term. This is a T final here, and we're going to kind of feed the chickens. So expand on these brackets here. So this will be, and I'm also going to factor at the same time. So let me know if this is confusing. I could put in the comments what I did, kind of step by step, a little bit more. But I'm good, just to save space here, I'm going to distribute this in and factor at the same time. So if I do that, this will be 418.6. Plus 96.278 and plus 14.3, and this is all joules per degree Celsius, right? I'll put the units there, and then this is T final because I factored out T final, and now we have, so 418.6 times negative 15. I'll just say 15, knowing that it's negative. So that's negative 6279, negative 6279. Degrees Celsius cancel out, so we're in joules. See, degrees Celsius cancel out, so we're in joules. This times 85, so 96.278 times 85 is 8183.6. minus 8183.6, and degrees Celsius cancel out, so we're left at joules, which is good. And then this term here we can finally fit on the same line, minus 214.5 joules equals 0. Okie dokie, so minus 26278.79 minus 8183.6 minus 214.5. Oh, that's a 6 there. Make it a 5. It's not going to matter, but Okay, so 14677.1, 14677.1, and we're in joules, which is a good sign. We'll transpose this to the other side and divide by this number so that we can solve for T final, and that's 14677, just double checking, 677.1 joules over 529.178 joules per degree Celsius. And before we calculate it, it's nice to check out our units. Joules cancel. We're left with 1 over degree Celsius in the denominator. So if we kiss and flip, this unit becomes on the top. So it becomes degrees Celsius. Okay, so we'll move that down, give us some more room. I'm always solving problems. I got the next one ready. Anyways, 14677.1 divided by 529.178 is 27.736. 27.736. Let's do blue. 27.736. 73, yeah, we'll round that to 6 degrees Celsius. And we'll do, actually, let's see if this makes sense before we do sig figs. Does this make sense? It's 27, about 28 degrees Celsius. This is at 85. So we have 85 degrees Celsius adding to 15 degrees Celsius. Our final, our T final is approximately 28 degrees Celsius. Well, it's closer to the 15 degrees Celsius, which makes sense because we have a greater mass of water. So because we have a whole 100 grams of water at 15 degrees Celsius and only 23 grams at 85 degrees Celsius, we expect the final temperature to be closer to this one here, the 15 degrees, than to this hotter one here. Plus, the calorimeter is drawing energy away as heat. We have heat transfer into the calorimeter, which is going to decrease the final temperature as well, because this calorimeter is going to absorb some of this energy as heat, which is going to kind of reduce the overall temperature as well. So that does make sense. And sig fig. So we have 4, we have 2 in the temperature, and we have 1 decimal place, 2 sig figs here. So this is a whole number. It's 1, 2, 2 sig figs. So these numbers here only have 2 significant digits of significance. This is 85. So, and then this one has, I think this one has a lot. Oh, this one's 2. So this one only has 2 as well here. So we're in this number here 2. So if we add this up, it looks like this only has 2. No, we have 3 sig figs here because we're adding an extra decimal. See, this is the place value is in the hundreds place value. That's our least significant digits, or hundreds place value is least significant. And what about over here? We have, where did this number come from? Oh, we have 4 sig figs here and 4 sig figs here. So 4 sig figs, 96. Where did the 96? Oh, it came from the 23. So this is 3 sig figs. So we have 3 sig figs here, adding it up to this. This is here. So 1 decimal. So we actually have 4. So we have 3 sig figs. We have 3 significant figures according to the kind of the quick and dirty sig fig rules. So our final temperature is 27.7 degrees Celsius. Hope that makes sense. Let me know if I made an error, but I think that's right. And that's it. Final temperature of the water. Hope you enjoyed it, everyone. Thanks for watching. We went through many different techniques. I got many videos on thermodynamics and other areas of chemistry, math, and physics. So check those out. Cheers.